Welcome back to the Quantum Rings Quantum Summer School. Today, we're finally getting to Shor's algorithm. We're first going to talk about RSA key encryption and understand how that works, and then we're going to understand why Shor's is a threat to that. Shor's, as we're going to learn, is just a special case of quantum phase estimation, which we learned last week. Let's get into it. So we're going to start off by talking about RSA encryption, how that works, and then we're going to talk about Shor's algorithm. Talking about RSA encryption is important because we want some context for why Shor's algorithm is such a huge deal and why you may have heard of it before and its impacts that it may have on our current encryption schemes. So RSA, which is named after these three people, essentially works like this. We have our two friends, Alice and Bob. Alice has some information that she wants to send to Bob, but she wants to encrypt it before she sends it. So half of RSA is a public key, which is composed of some number n and some number e. And Alice is going to use n and e to encrypt her data. So she uses the public key to encrypt her data. And then she's going to send it over to Bob. And Bob is going to use a private key to decrypt the data. And the private key is also going to be n and then another number d. And at the end, Bob will have recovered the same info that Alice originally sent. So two components of RSA are a public key and a private key. And only Alice and Bob are supposed to know the private key, but anyone else can know the public key. So one question you may be wondering is, it's public knowledge how Alice encrypted her information. She used the public key N and E. So why can't anyone just decrypt the data if they know how she encrypted it? And the reason that it's safe from an eavesdropper just decrypting the information is that large numbers are really hard to factorize. So if you have some number n, which is a product of two primes, p and q, it's really hard to factorize that into its two primes. It's also very easy to find large prime numbers, so it's very easy to come up with a p and q, which are, let's say, hundreds of digits long, but it's really hard to take an n, which is hundreds of digits long, and factorize it into two primes. So to get a sense of how RSA works, I first want to talk a bit about modular arithmetic. So modular arithmetic, you can kind of think of it also as arithmetic on a clock. So basically, if you keep counting up and up, eventually you'll cycle back around and keep going in a circle. If you have any integer a, this is any integer, then we can say that it's equivalent to another number b mod n, where n is any natural number. So this would be 1, 2, and so on. And b is going to be some number which is 0, 1, 2, all the way up to n minus 1. So it's just a way to reduce a number modulo another number. So some examples, we could have 7 mod 3. So if we start at 0 would be 0 mod 3, 1 is 1, 2 is 2, and then 3 would be 0 mod 3. 4 would be 1 mod 3. 5 would be 2 mod 3. 6 again would be 0 mod 3, and then 7 would be 1 mod 3. So we're basically just going around in a circle. If a number is a multiple of what you're taking modulo by, then it's going to be 0. So for instance, 8 would be 0 mod 4. And then just as another example, to check yourself, what would 8 be mod 5? It would be 3. So the basic premise behind RSA key generation, so this is how we generate the public key and the private key. We're first going to pick two large prime numbers, p and q, and then our number capital N is just going to be p times q. Then we're going to compute this value, lambda of n, which is called the Carmichael's totient function. And because n is a product of two primes, this totient function ends up being the least common multiple of p minus 1 and q minus 1. Then we're going to choose our encryption exponent e to be some number that's greater than 1 but less than lambda n. And then finally we can compute d. D is going to be the modular inverse of e mod lambda n. So this is just a notation for it. So d is equivalent to e to the minus 1 mod lambda. But this is really just saying that if you multiply d times e, then that's going to be equivalent to 1 mod lambda. So it's just a multiplicative inverse. So now we have our keys, the public key and private key. How do we use them? So let's say we have some data, which I've put here as capital D. Then to encrypt the data, which I'll call capital E, this is just going to be d to the e mod n. And then to decrypt the data, we would take capital E to the d, our decryption exponent. This is the same as d to the e to the d. And this is going to be equivalent to d mod n. And the reason why this works is due to this little theorem, which is that if a and b are equivalent mod lambda and c is coprime to n, then the following is true. C to the a is equivalent to c to the b mod n. And what I mean by coprime is that they share no factors. So for example, 8 and 9 are coprime because 8 is equal to 2 times 2 times 2, and 9 is equal to 3 times 3. So the greatest common denominator of 8 and 9 is 1, or greatest common divisor. In our RSA encryption scheme, we have that DE is equivalent to 1 mod lambda. So we're going to have d to the DE equivalent to d to the 1 mod n. One problem that we have here, which is not a problem at the moment, is that if you know p and q, you can very easily compute the totient function, because that's just the least common multiple of p minus 1 and q minus 1. And then d is just the multiplicative inverse of e mod lambda. So if you know p and q, you can very easily compute lambda n and then learn the private key, and then you'd be able to decrypt the data. So RSA only works because we rely on the fact that given n, it's super difficult to find p and q, virtually impossible. That's where Shor's algorithm comes in. But first, let's move to the coding notebook and take a look at RSA key encryption. So the first thing we want to do is import all the libraries that we need. And then we also have some helper functions here. So here we have a helper function for modular exponentiation. So instead of just computing some number x to an exponent and then reducing it mod n, instead we're going to multiply by x, reduce mod n, multiply by x, reduce mod n, e times, where e is the exponent. And this just reduces the computational overhead and makes it a lot faster. Then we also have a mapping function to map from integers to exponentiated things. So we provide a number b, and then it returns back a to the b mod n. And this is going to be very useful for Shor's algorithm later. We also have this function, which I called quasi-modular exponentiation, and I'll discuss this more when we get to Shor's algorithm. And then this is a helpful plotting function that, again, I'll explain when we get to Shor's algorithm. Let's try out RSA key encryption. So the first thing we want to do is pick two large primes, and you can find a Wikipedia list of prime numbers. Just grab any two that look good to you. And then our n is going to be p times q. And our lambda is going to be the least common multiple of p minus 1 and q minus 1. Oops. So here's our n, and here's our lambda. Now we want to pick a random e somewhere in between 1 and lambda. So I'm just going to loop through a bunch of times, each time pick a random integer, and then we want to check that e is coprime with lambda. So coprime just means that their greatest common divisor is 1. So we're just going to check if the greatest common divisor of e and lambda is 1, then we're going to break out this for loop, and that's our e. So here's our e. And then we want to get the modular inverse of e. Okay, and that's our d. It's just the multiplicative inverse of e mod lambda. Now we can pick a message of our choosing. So for instance, my message might be hi, and then we can turn our message into an integer by using ASCII keys. So I'm just converting, so for instance, h is 104 and I is 105. And then our encoded message is going to be modular exponentiation of our message with the encryption encoding exponent mod n. So here's our encoded message. And then to decode, we're just going to do another modular exponentiation, and then we're going to be exponentiating e to the decryption exponent mod n. And we got back our original message, which is hi. So if you want, here's some challenge problems just to play around with other values of p and q and other messages. And then think about what happens if the message is a larger integer than n. And then just remind yourself, why is it a problem if the eavesdropper can factor n into p and q? So now let's get to the exciting part, which is Shor's algorithm. The goal of Shor's is that if we're given a non-prime number n, we want to factor it into the product of two numbers. So n equals a and b, with a and b being somewhere between 2 and n minus 1. So for example, if we had n equals 12, then for instance, we could factor it into n equals 3 times 4. And these numbers, a and b, might not necessarily be prime, but we could go further with it. So we say, okay, 3 is prime, but 4 is not. And then we could break down 4 into 2 times 2. So you can kind of do this recursively to break a number into all of its prime factors. But in our case, we're going to be working with an n that is p times q, where those are both primes, so we'd only need to do this once. So what is our approach going to be? We're going to choose an a that is somewhere between 2 and n minus 1, which is coprime with n. So remember, coprime means that their greatest common divisor is 1. So a fact is that if a and n are coprime, then there necessarily exists an integer m such that a to the m is equivalent to 1 mod n. And we can choose r such that it's the smallest possible m that satisfies this condition. So then we have a to the r is equivalent to 1 mod n. So this means if we subtract 1 to the other side, we can actually factor this into, I always forget the name of this. It's like the sum and difference of squares. So we can FOIL this out into a to the r over 2 minus 1 times a to the r over 2 plus 1. And since we just subtracted from both sides of this up here, a to the r minus 1 is going to be equivalent to 0 mod n. So if r is odd, then a to the r over 2 plus or minus 1 is not necessarily an integer. So if that's the case, we're just going to retry. So go back to the start and pick a different a, try again. If r is even though, then a to the r over 2 plus or minus 1 is an integer, and we can continue. So we said that this value, a to the r over 2 minus 1 times a to the r over 2 plus 1, is equivalent to 0 mod n. So that means that n divides that number. So I just want to note here that it can't be the case that n divides a to the r over 2 minus 1, because that would mean that a to the r over 2 is equivalent to 1 mod n. But we said that r is the smallest possible number for which that is true. We know that n does not divide a to the r over 2 minus 1. So now there's two other cases. So first case is that n divides a to the r over 2 plus 1. Then that means that we did not actually learn anything about the factors of n, because a to the r over 2 plus 1 is just some multiple of n, and we did not learn anything new. So if that's the case, just go back to the beginning and pick a new a. But if n does not divide a to the r over 2 plus 1, then they share a common factor. And this factor is not going to be 1. Well, of course, every integer shares a common factor of 1. But n does not divide a to the r over 2 plus 1. So they have to share a common factor, which is not 1. So we can pick our first factor to be the greatest common divisor of n and a to the r over 2 plus 1. And then the other factor would just be n divided by f1. So that's how we find the two factors of n. So this is all well and good, but what is the hard part, and how does Shor's algorithm help? So the hard part here is finding r. So for Shor's algorithm, we're going to be given an n. We're going to pick an a and compute r. This is the hard part, and this step is called quantum order finding. Then if r is odd, we're going to go back to step 2 and pick a new a. If r is even, then we're going to compute the greatest common divisor of n and a to the r over 2 plus 1. If that greatest common divisor is n, then we need to go back to step 2. Otherwise, that and n divided by that are your two factors. So now let's talk about the hard part, which is the order finding. So here's an example where n equals 15 and a equals 7. And we can consider raising 7, which is our a, to the power of something mod 15. So just as a reminder, this is a to the b mod n. And we can see that 7 to the 0 is 1 mod 15, 7 to the 1 is 7, 7 to the 2 is 4, 7 to the 3 is 13, and 7 to the 4 is 1. Okay, so now we can see that the smallest possible natural number, such that 7 to that number is 1, is going to be 4. So r equals 4. And if we look, we see that this keeps repeating itself. So at 2r, which is equal to 8, 7 to the 8 is also 1. And this happens again at 3r. So what we have here is a periodic function. And what tool do we have for detecting periodicity? We have the quantum Fourier transform and also quantum phase estimation. These are the two tools that we learned last week that are really helpful for finding the periodicity or frequency of something. So here's the whole algorithm. We're going to start off with two registers. So here, this upper register we can call the source, and this lower register we can call the target. So in the source register, we're going to prepare everything into the equal superposition state. So we're going to apply a Hadamard gate on all the qubits so that at this point in the circuit, it would be in the equal superposition of all bit strings of length n. And then we're going to apply this giant unitary. And then finally, at the end, we're going to apply the inverse quantum Fourier transform on the source register and measure the source register. So this unitary performs modular exponentiation. So if we input x in the source register and y in the target register, then after applying u, we would still have x in the source register, but now in the target register, we would have a to the x times y mod n. And if we input y equals 1, then it would just output a to the x mod n. So the target register should be initialized in the 1 state. So that's where the string is 0, 0, 0, etc., 0, 1. So how do we construct u? So we can decompose x in binary. So if we have x in base 10, then we can break it up into its digits. So that would be like xn minus 1 all the way down to x1, x0. So each of these is 0 or 1. And then we can express x as x n minus 1 times 2 to the n minus 1 plus so on and so forth, x1 times 2 to the 1 plus x0 times 2 to the 0. So we can rewrite a to the x as a to all of that, and then if we have sums in the exponent, we can just break that out into multiplication. So we can think of this as having like n different steps. So we can define a smaller unitary, which we'll call UA, and we can say that the function of UA is to send y to a times y mod n. And then that means that if we do this unitary UA 2 to the j times, then we're going to multiply y times a to the 2 to the j. So I also just want to point out here that you could also express this as u of a to the 2 to the j. They're equivalent. So now we can break our unitary down into n different steps. So first we would do x controlled on x0, ua to the 2 to the 0. So let's just go through step by step, and let's consider just this source register y. So at first, this source register is just going to be in the state 1. So it's all zeros and then 1 at the bottom. And then at this point, after we've controlled on the state of x0, doing this unitary u to the a to the 2 to the 0, we're going to multiply it by a x0 2 to the 0 mod n. Then after the next one, we're controlling on the state of x1 and doing u of a to the 2 to the 1. So at this point in the circuit, we're going to get an additional factor of a x1 2 to the 1. This is a x0 2 to the 0. And if we keep doing this all the way up through x minus 1, then at the very end of the circuit, we're going to have a to the x mod n. So this is essentially our giant unitary u. It can be broken down into n different steps. So now a claim that I want to make is that lambda k equals e to the 2 pi I k over r is an eigenvalue of ua with the following eigenstate psi k. And just as a quick reminder, an eigenvalue and eigenvector, so for instance, if we have some operator or matrix A acting on a state psi, and we get back a scalar times psi, then this is an eigenvalue, and this is an eigenvector. So the details here are not super important. If you're curious about the math, it's worked out here, but you can also just take away the quoted end result. So here's our psi k. It has this 1 over root r out front for normalization, and then it's a superposition of states, which is a to the j mod n, where j ranges from 0 to r minus 1. And then it also has this phase factor out front. So if you apply ua to that state, you'd end up, I'm just plugging in what ua does. It just multiplies by a. So this exponent j became j plus 1. And then in this next step here, I'm just pulling out a factor of e to the 2 pi I k over r out front. And when I do that, this j here would become a j plus 1. And then we can note the fact that a to the 0 is equivalent to a to the r is equivalent to 1 mod n, because we know that by definition a to the r is 1 mod n. And so it doesn't matter if we're counting over j or j plus 1, it's all going to be the same. So that is just, this whole thing here is just psi k. So we can see that ua times psi k equals this lambda k psi k. So now the next thing that we need to notice is that the structure of Shor's algorithm is exactly the same as quantum phase estimation, which we learned last week. So let's remind ourselves about quantum phase estimation. So for quantum phase estimation, we had a bunch of qubits in the 0 state. We apply a Hadamard to all of them to put us in an equal superposition of all bit strings of length n. And then we had some other register with a bunch of qubits, and we did a bunch of controlled unitaries. So we had some unitary u, and then we applied controlled on one of the qubits, u to the 2 to the 0, and then on the next qubit, u to the 2 to the 1, and the next one, etc., all the way up to the n minus 1 one. And then finally at the end, we performed the inverse quantum Fourier transform and measured all of the qubits. So last week, what we saw was that this u that we applied sequentially to higher and higher powers, our u had an eigenvalue of e to the 2 pi I theta. And at the end of the circuit, when we finally measured, we got an n-bit approximation for theta. So what the quantum phase estimation algorithm does is it takes some unitary with an eigenvalue, we apply it sequentially, controlled down the line, and each time to a higher power of 2. At the end, we measure the phase of that eigenvalue. So that was last week. And now today, our u has eigenvalues e to the 2 pi I k over r and eigenvectors psi k for k equals 0, 1, all the way up to r minus 1. So what we're going to expect to measure at the end of the circuit is an n-bit approximation for k over r, for one of the k. If we do this many times, we should tend to measure a distribution which is higher in probability to measure k over r. So I just want to emphasize here that Shor's is just a special case of quantum phase estimation with a special unitary. This is super similar to what we learned last week, but now we've just changed the unitary. So again, the expected result at the end is that we're going to measure an n-bit approximation of k over r for k in 0, 1, all the way through r minus 1. And I'm putting this 2 to the end here because we're going to consider our results in terms of integer values. Last week we talked about it in terms of binary decimals. Either way is fine, but for today we're going to do this way where it's the 2 to the n k over r. So then if we measure many times, we're going to measure multiples of 2 to the n over r with high probability. So here's an example of something that we might measure. So we have some probability distribution. We're always going to measure 0 because k can be 0. So 2 to the n 0 over r is 0. But then we'll measure some lower probability on other numbers, and then it will spike up again, and then go back down, and then spike up again. It's going to be periodic. So in this case, with this measurement distribution, if n was 3, then we can see here that we had a peak at 4, and this peak ought to be at 2 to the n times 1 over r. So this is 8 over r, and we can conclude that r equals 2. If n was equal to 5, however, and we got this measurement result, then 4 again would be 2 to the n times 1 over r. And we would conclude that r is equal to 8. There's a more systematic way to go about this called the continuing fraction algorithm. So this is kind of a hand-wavy approach to get at the periodicity. There's definitely a more systematic way to do it, but just to get an intuition for today, this is what we're going to do. So the complexity of Shor's is order log n cubed. And what is the bottleneck here? Well, the hardest part is making that unitary UA. And in general, those controlled unitaries, which is like UA raised to different exponential powers. So in order to make UA, we can construct it out of other things. So to make UA, we would need a bunch of multi-targeted C0 gates. And then also as a controlled multiplication and addition mod n. So this would take in 2 registers, x and b, and then would return x and then b plus ax mod n. And so we actually need an additional register of qubits just to make the MAs possible. Then we can break down those MAs further into QFTs and addition mod n's. And then addition mod n can be broken down into QFT, controlled Z rotations, and C0s. So you can see that just one UA is going to be composed of a ton of different gates. And that's how the complexity of Shor's grows. The other parts of Shor's algorithm are the inverse quantum Fourier transform and then classical pre and post processing. And these are all much faster than the controlled unitaries. But compared to the best classical algorithm, which is the number field sieve, the complexity of that is super polynomial time, but sub-exponential. So it's unreasonably long, basically. So Shor's is polynomial time, and it's an exponential speed up over the best classical algorithm. So whereas it's virtually impossible to factorize n into p and q classically, with Shor's, it's actually a very attainable thing. So now let's go back over to the coding notebook. So first, let's factor n equals 15. We already know what we expect as a result, 3 and 5. And we just need to pick an a. So I've picked a equals 7 because I know that it's going to work out, but you can also explore with other values as well. And then we want to find the period r of the function a to the b mod n. So we can take a look at this function. We can construct the mapping from using n and a, and then I want it to print out. So just make this true. I forgot to run these cells. Make sure you run all the cells at the top. Okay, so we're going to construct our mapping. And we actually already had this written down in the part where I was writing earlier, but just printing it out again. So we have this periodic function, which has a period of 4. So at b equals 4, b equals 8, b equals 12, we return back to 7 to the b equals 1 mod 15. So we already know that r should be 4. And we can run Shor's algorithm with n equals 4 qubits because 15 is less than 2 to the 4. And we're going to expect to see measurement results at multiples of 2 to the n over r. So 16 over 4, so this should be at 0, 4, 8, 12, etc. So one thing I want to point out here is that when we set up this Shor's algorithm, we're not actually going to construct the unitaries UA. Instead, we're just going to implement a quasi-modular exponentiation where we provide it with this mapping, and then for any input b, it maps it to the corresponding output. This is basically cheating because we already know what r should be and we're providing the mapping ahead of time. But this is just because today is about gaining an intuition for how Shor's works and not so much about getting into the weeds of quantum modular arithmetic. So let's do it. So our source register is going to have 4 qubits. The total number of qubits is twice that because we're also going to have our target register. And we can create a quantum circuit from that. Then we want to create an equal superposition state in the source register. So we want to apply a Hadamard gate to everything in the source register. Then we want to apply the modular exponentiation unitary. So we're going to compose that in place. So this is going to be quasi-modular explanation. We have our mapping from before, and the number in the source register. And we're just going to convert this to a gate. And we want in place equals true because we want to modify the current quantum circuit object and not create a new one. And then we want to perform inverse QFT on the source register. So we want to perform QFT on source register, and we want it to be the inverse, so inverse equals true. And then there's another parameter here called do swaps, and that's if you want to reverse the bit ordering. And I can't remember if that's defaulting to true or false, but it should be false here. And we also want this to be in place. So let's see our circuit. So here we have it. We're putting the source register into the equal superposition state. We're applying our modular exponentiation unitary, then we're applying inverse QFT, and finally measuring our source register. We can transpile the circuit so we can run it on the quantum rings backend. And then I'm going to print out the probability distribution. So before we said we should measure multiples of 2 to the n over r. We know that r is equal to 4. And we see that here. So we have 0, 4, 8, and 12. So this is great. This is working. We could also go backwards. So if we see the smallest non-zero high probability measurement result, which is k equals 4, then r would be 2 to the num source divided by k. So r is 4. And now we can proceed because r is even. Remember that if r is odd, then a to the r over 2 may not be an integer, so that's not good. But it's even, so we can continue. And that factor is going to be the greatest common divisor of n and a to the r over 2 plus 1. And then the other factor is going to be n divided by f1. So hopefully, if we did everything correctly, we get that the factors of n are 5 and 3. Okay, now let's do another example. So we could pick, for instance, a equals 17 for n equals 21. We know that the result should be 7 and 3, but let's try it out. So again, we can construct a mapping. So here we can see that r is equal to 6. How many qubits do we need? Well, 4 is not enough because 21 is greater than 16, so we actually need 5 qubits. And then we can do the exact same thing as before and run the circuit. Okay, so this looks a lot different from before and maybe a lot less obvious. But we can see a peak here at 0. We can see another peak around 5-ish, 11-ish, 16-ish, etc. And so it's actually helpful to plot, instead of k, the fractions k over 2 to the n. And we expect k over 2 to the n to be multiples of 1 over r. So we can plot this as fractions. And we know that our r is supposed to be 6. So we can kind of see how this distribution looks. And we can see that at multiples of 1 over 6, kind of clustered around that are higher probability states. So the reason that we're not getting exact answers is that 32 is not divisible by 6. So we're basically just getting an n-bit approximation of the answer that we want. So if we plug in r is equal to 6, unfortunately, we get that the two factors of n are 21 and 1. So that was useless. We didn't actually learn any new information. So we should try again with a different number. So if you picked 11, for instance, this also has r equals 6. And if we go through all the same steps, we get a similar distribution, very similar. And then we get that the factors of n are 3 and 7. So if you want an extra challenge, you can try and use Shor's algorithm to factor 33. So think about how many qubits do you need for that. And then you can try it out with different numbers and see which values of a work and which don't. Also, feel free to try other numbers too. Congratulations, you just learned Shor's algorithm, which is arguably the most famous and most well-known quantum algorithm there is. So far in this course, we've only been working with perfect ideal qubits, but that's not how it is in real life. So next week, we're going to talk about noise and error mitigation. I'll see you then.